Awesome. Okay, now our last problem of the day is sort of a doozy. It combines some of the percent composition work that we did in the earlier problems with empirical formulas. So you look at question number 4, it says a combustion device was used to determine the empirical formula of a compound containing only carbon, hydrogen, and oxygen. A 0.6349 gram sample of the unknown produced 1.603 grams of carbon dioxide and 0.2810 grams of water. Determine the empirical formula of the compound. So again, we're doing combustion here. We're assuming complete combustion. We're only going to get carbon dioxide and water as our products. And we're asked to figure out what the empirical formula is. So as you think back to the last problem, we need to know how many moles then of carbon, hydrogen, and oxygen we have in this sample so that we can then compare them to write our formula. We're going to start with carbon. Now, as you look at the problem here, again, we're only making carbon dioxide and water. So in our products, the only place that we see carbon is in the carbon dioxide. So we're going to determine how much of this 1.603 grams of carbon dioxide is carbon by doing a percent mass calculation. So the percent carbon in carbon dioxide, we take the mass of carbon, which is 12.01, which comes from the periodic table, and divide that by 44.01. So this is grams carbon. This is grams carbon dioxide. And again, where do these numbers come from? Our carbon, 12.01. Carbon dioxide is going to be 1 carbon and 2 oxygens, which is going to be 44.01. Which means that the percent carbon in carbon dioxide is 27.29%. And this is the percent carbon in any sample of CO2. Our sample is 1.603 grams. Therefore, if we had a 1.603 gram sample, only 27.29% of that 1.603 grams would be carbon. So we simply multiply this by the percent 0.2729. Again, I just moved my decimal 2 places there. To get us 0.4374 grams of carbon in CO2, but it's also the amount of carbon in our original sample. And again, as you think about how, in combustion, carbon dioxide and water are only 2 products. That carbon must have come from the carbon in our original sample. Again, the law of conservation of mass. We can't just create carbon out of nothing, so it must have come from the original sample. We're going to do the same thing with hydrogen, except recognizing that the hydrogen is going to come from the water. So your percent hydrogen in H2O is going to be 2.016 because there's 2 hydrogens. In every water. And again, that 18.016 is going to come from the periodic table. This time we're doing water. H is 1.008. H2O is going to be 1 of these and 2 of these and 1 of these to give us the 18.016. Which means that our percent hydrogen in water is 11.19%. And again, any sample of water is going to have 11.19% hydrogen by mass in any sample. of H2O. Therefore, in our sample, we have 0.2810 grams of H2O. Therefore, we have 0.2810 grams of H2O multiplied by that 11.19%. Again, remember, when we're multiplying by those percentages, we move our decimal by 2 place values to give us 0.03144 grams of hydrogen in the H2O that was formed. And again, that also means that 0.03144 grams of hydrogen came from our original sample. Whew. Okay, quick breath. So if you're really excited to do this again with oxygen, you're going to be disappointed. We don't have to do this again for oxygen / it's difficult because we're burning it in oxygen, so we're not sure how much came from the oxygen that was burned in and how much came from our original sample. It's actually, though, a little bit easier. In order to determine the amount of oxygen that we have, all we need to do is take our original sample mass of 0.6349 grams and subtract the mass of our carbon, which we determined earlier to be 0.4374 grams, minus the mass of our hydrogen, which is 0.03144 grams. And because the original compound only consisted of hydrogen, carbon, and oxygen, whatever's left over must be the mass of oxygen that was in our original compound. So we get 0.1661 grams of oxygen in original compound. Original sample. Same difference. Whew. Okay, all this work and we haven't answered the problem or answered the question. We're asked to determine the empirical formula. While we know masses in grams, keep in mind empirical formulas are showing us the ratios of moles, the smallest ratio of moles. So we just need to convert all these grams now to amounts in moles, compare them, and figure out what our formula is going to be. Easier said than done. Again, we're going to start with carbon. We determined that our carbon sample had 0.4374 grams of carbon in the original sample. We're going to do a quick conversion to moles by using the molar mass found on the periodic table, which means that we've got 0.03642 moles of carbon. With hydrogen, we determined that we had 0.03144 grams in our original sample. Converting to moles of hydrogen, whoa, error. We get 0.03119 moles of hydrogen. And then finally with oxygen, we determined that we had 0.1661 grams in our original sample. Converting to moles of oxygen, gives us 0.01038 moles. Now, again, empirical formula is just a ratio or comparison of these three different numbers of moles. It's a little more difficult to compare these numbers than it was in the earlier example. Any situation like this, you just need to find the smallest number of moles and divide each of them by that number. In this case, it's going to be our number of moles of oxygen. And when we do that here, we get approximately 3.5. We get approximately 3 when we do that here. And we get exactly 1 here. Which means, therefore, that our formula is C3.5H3O. Woo! Right? Close. Remember, it's smallest whole number ratio, so just remember, or just think to yourself, what can I multiply each of these numbers by to get me whole numbers, so that they're all whole numbers? Looking at your decimal, or for the fraction, if we multiply each of those by 2, C7H6O2, there's our empirical formula. Wham, bam, thank you, ma'am. Done.